Nils from HuggingFace. And so his research focuses on representation learning and neural research. Actually, he didn't write about his previous academic career, but I can shortly tell that he did his PhD and postdoc at UKP TU Darmstadt, and now he's leading a research team at HuggingFace. And his sorry. Yeah.
Okay, great.
No, just give me a minute. So during his postdoc at the UKP Lab at TU Darmstadt, he authored Sentence-BERT. It's a very popular GitHub repo, actually. I'm sure everyone has heard of it. So it resulted in the popular sentence transformers library, and people use it like every day to compute state-of-the-art text and image embeddings. And he focuses on making text embeddings and neural search more widely accessible with a focus on domain adaptation and multilinguality. And recently he joined HuggingFace to lead the research team on neural search and to further enhance sentence transformers. Okay, Nils, the stage is yours. We are excited to hear about your talk.
Yeah, great. Thanks for the invitation. Really happy to present my work on neural search. In case you have any questions in between, feel free to ask them. So I think we can make it quite flexible here. So I cannot really see the chat when I'm presenting. So if there are like any interesting questions I should answer, someone would need to unmute.
I will do that.
And ask the question. Yes, so I don't know how much you followed information retrieval, but there was like I would call it the winter of information retrieval. So I hope people from the IR community will not kill me for this phrase, but there has been, from my outside perspective, not any progress made in the last 20 years or so in information retrieval. But luckily, in the last few years, we see quite a lot of progress in terms of information retrieval, and now information retrieval also in the NLP community at ACL, for example, where NLP became like a really hot topic, and the results and systems got so much better. And today I would present like an overview of neural search, like what are different architectures, pros and cons, and how can you combine them in a smart way to improve the systems to get the best system possible. So to start, I want to show like a real example why neural search is so much better than the traditional search. So here, for example, imagine you have your Wikipedia, you're the Wikimedia Foundation, and you want to create like a search function for Wikipedia. And if you do this with classical lexical search, the results are pretty bad. So for example, if someone is searching for what's the capital of the United States, and then you do this with lexical search using BM25, the #1 hit is about capital punishment in the United States. And the second entry is about Ohio, because Ohio is a state in the United States, also has a capital. And the third entry is Nevada, because it also mentions United States, that it's a state, and also has a capital. So all three hits you get from any lexical search system which has been used over the last, I don't know, 20, 30 years, or maybe even 50 years, are really disappointing for the user. However, if you turn to a really simple neural search system, which is based on a neural network, you get quite interesting or quite good results. So the first result is about Washington, DC. So that's exactly what the person was looking for. The second entry is about a capital city, or how is a capital city defined? And the third entry is about the United States Capitol, because maybe the person has misspelled capital with Capitol. So the results are a lot better in terms of user's perspective, but also you can put it in terms of benchmarks. I mean, we're in machine learning, we love benchmarks. And there's an old benchmark from 2004, the Track Robust 04 dataset. And the black line is like the best system from 2004. And as you've seen, from 2004 to 2018, like 14 years, there's like not really any progress. So systems 14 years later are just as good as a system which was originally handed in 2004. But then pre-trained transformers entered the field, and we got quite a nice improvement in 2019, even more improvement in 2020, and more improvement in 21 and 22. So a lot of progress has been made in the last 3 years. Today, I want to present different architectures. So for neural search, there are like a large number of architectures, which I'm not able to cover them all. So here I want to focus on like 3.5 different architectures. The first architecture is doc-to-query, where you use an encoder-decoder architecture to take the documents and you predict queries, what people could search for. Then I want to present cross-encoders, which takes the query and takes the document and does cross-attention between the query and the documents. And then there are bi-encoders, which treats the documents and the queries independently. And here we can differentiate between dense and sparse. And during the talk, I want to give a highlight of these architectures, as I think these are the most relevant and important architectures. I want to talk about strengths and weaknesses of these architectures, and then how can you combine the strengths of different architectures to get the best search experience possible. So the first one is doc-to-query, which I think it's a really nice and simple idea. So what you have in search, you have some documents. For example, in Wikipedia, you have the hundreds or millions of documents, articles. And what you use here is an encoder-decoder architecture, for example, T5. And you take the document and you predict the queries. What are people searching for? So for example, here we have the document, researchers are finding that cinnamon reduces blood sugar levels. And then you predict, okay, someone could search for, does cinnamon lower blood sugar? And this person would be happy to retrieve this document. And you predict a lot of queries, like, for example, 40 queries per document. And then you concatenate them, you put them in a lexical search index. And then when someone search for it, foods and supplements to lower blood sugar, you not only search the document, but you also search the predicted queries. And it has been shown that this improves the documents you retrieve from your index. Second architecture are cross-encoders. So this is also quite an old architecture, which was published shortly after the BERT paper. The cross-encoders, they work in 2 stages. So first you have first stage retrieval. So you have your search query or some question. You have your document collection with all the articles from Wikipedia. And then you do a first stage retrieval. So from the 5 million articles in Wikipedia, you somehow have to extract a smaller candidate set. So for example, 100 candidates. And here you can use lexical search, for example. And then you take the smaller set and these 100 documents and you pass it to the cross-encoder. And what you do is you concatenate the query and the document, you feed it to a transformer network, and then you have a classification head on top, which outputs some score between 0 and 1, indicating how relevant is the document for the query. And then you can sort by this output. So you do this for all the 100 documents you retrieved from the first stage retrieval, and you just output the top 10. And the final architecture I want to present are bi-encoders. So bi-encoders, they work in terms of vector spaces. So you take all your 5 million articles from Wikipedia, you encode them in the vector space. And then when there's a new query, like what's the capital of the United States, you encode it in the vector space. And then you do nearest neighbor search. So you look for the documents which are closest to the vector of the query. And these are hopefully the relevant documents for the query. So in terms of the architecture, it's also quite simple. In contrast to the cross-encoder, here you have like 2 ways to encode. You have the query and the document. You pass them individually to the transformer network. You do some pooling operation, and this gives you a fixed sized vector at the end, which you can then compare with cosine similarity to give you the similarity between the query and the document.
Nils, can I interrupt?
Sure.
So bi-encoders are basically later than cross-encoders, or are they introduced around the same time?
Yeah, I mean, bi-encoders, they exist for a really long time. So that's, I don't know, probably like 10 years, 20 years. So I don't know when people started to introduce it, but the idea is like really, really old, that you encode it individually. So basically also like TF-IDF or BM25 are also basically bi-encoders. So when you do TF-IDF, you compute the TF-IDF from the document, you compute the TF-IDF from the query, and then you compute the cosine similarity. So the idea is like 50 years old, or maybe even older. What just has changed is how you encode it. So going from TF-IDF, and then people used, when neural search or neural networks started to get traction, use word embeddings and CNN and LSTM, and now they are using transformers. So the idea is quite old. And using BERT for this, or some transformer network, was also published shortly after the BERT paper appeared.
Yeah, so in scope of neural search, I guess first they introduced having BERTs in bi-encoder idea, and then we had the cross encoders, right?
Yeah, it was really similar in time. So both bi-encoders and cross encoder both appeared in 2019 using BERT.
Okay, thanks.
So there's like no real timeline between these architectures. Yes, so bi-encoders, they are also quite interesting because they can overcome issues with modality and multilinguality. So if you do lexical search and you search in Turkish for German documents, you will basically not find any results. And with bi-encoders, if you have some shared vector space, it doesn't matter what's your input. You can input images and text. So when you search for 2 dogs in the snow, you can find this image. Or you can also align the vector spaces so that it's independent. If you search in German, English, or Chinese for 2 dogs in the snow, you will still find this image or any documents. So that's the nice property of these bi-encoders, that they're not necessarily limited to language or to a specific language. So starting with understanding pros and cons. So over the remaining of the publication, you will see that cross encoders perform extremely well. So they are by far the best system for neural search, but they have a big issue that they are really, really slow. So imagine you have the search issue and you want to search over Wikipedia, and your query has 10 tokens and documents. So if you take Wikipedia, you break it down to individual paragraphs. So the paragraphs have on average 240 tokens, and you want to re-rank 100 documents. For a bi-encoder, it's quite easy. You just compute the embedding for the query. So for these 10 tokens, this maybe takes 10 milliseconds, and then you can do the operation in the vector space and find the closest neighbors. For the cross encoder, you first get like 100 candidates from, for example, lexical search, and then you need to concatenate the query with the documents and compute the score using cross attention. And so you have 100 documents, which has like 250 tokens both. And as we know, for a transformer network, the runtime grows quadratic with the number of tokens. So a forward pass of 250 tokens takes roughly 625 times longer. And if you multiply it with your 100 candidates, then you see that the cross encoder is roughly 60,000 times slower than the bi-encoder. So with the bi-encoder, you get your results, for example, in 10 milliseconds. With the cross encoder, you have to wait quite a long time until you get the search results. And in search, it's quite relevant to be not only precise, but also be fast. So if you type something into Google or into Amazon search, you don't want to wait 6 seconds or a minute to get your results, but you want to get it within like 10 milliseconds. Another disadvantage of cross encoders is that they still require first stage retrieval systems. So you still have you need some way to narrow down the 5 million documents you have from Wikipedia to like the 100 documents you want to re-rank. And here's the question, what do you use for first stage retrieval? And if the first stage retrieval does not find the relevant document for the user, you can also not re-rank this document to the user. So it will not appear in the search results. So even such that cross-encoders are really good, they are really slow, and they have this limitation that they only can re-rank what the first stage retrieval system has found. So that's why in production, people use bi-encoders quite often. But bi-encoders, they have many issues I want to address now in this talk. And I want to present how you can use the cross-encoder to improve the bi-encoder performance. So for bi-encoders, you can differentiate between dense and sparse bi-encoders, depending if they output a dense embedding or a sparse embedding. So dense embedding, you take your query, you pass it to the BERT network. BERT does output contextualized word embeddings for all your tokens in the query. And then you can do, for example, a mean over these tokens. And then you get a 768-dimensional vector space, which is a dense vector. So every dimension is non-zero. And you can do find the nearest neighbors in these vector spaces. And these dense embeddings, they have the advantage that they can overcome the lexical gap. So when you do lexical search, it makes a difference if you search for US, USA, or United States. So all three are different terms, different words. And if you search for United States, it will not find any documents for US. But a dense vector space can just embed all these three phrases to the same point in the vector space. And so it doesn't matter if you search for US or USA or United States. Also, dense bi-encoders, they can respect the word order. So previously, this has also not been possible with lexical search. So if you search for visa from Germany to Canada or visa from Canada to Germany, these are different intents from the user, and they want to see different search results. But with lexical search and a back of word search, they are both the same. So they do not respect the word order. But in a dense vector space, you can encode it to different points in the vector space. Also, it can know about related terms. So for example, if you search for Spearman correlation in NumPy, but the only document you have is like Spearman correlation in SciPy, the system can learn that NumPy and SciPy are really similar packages, and you can often use them interchangeably. So it can find documents which is not really 100% precise on your search, but which are related and also relevant for the user. What became popular in the end of last year are sparse bi-encoders. So this is a more recent development. Here you take the query, you pass it through the transformer network, and then you do a projection to a sparse vector space. So in a system, or in the state-of-the-art system, SPLATE, what they use is the vocabulary from the BERT tokenizer. So as you know, BERT tokenizes your text using a vocabulary of 30,000 entries. And then it projects the output from BERT back to these 30,000 entries, so that every entry corresponds to a word piece from the input. And it's a sparse vector, so not all the 30K entries are non-zero, but only few of them are non-zero. So only few of them have a value larger than 0, which we want to have them associated with the query. And for example, if you type in how to learn Python in such a system, it will output you a sparse vector with Python. So Python is the most important term. So it has like 2.7 relevance. But then it also includes guide, because documents where you can learn Python from, they are often like beginner's guide for Python. They can include also include the word learn and the word teach. What can happen is that you sometimes add, or that the model hallucinates, so that it adds terms which are hard to interpret. So for example, the model adds like this bracket to it, also with like a really high relevancy, really high importance, so even more importance than teach, which is like for us as human really hard to understand how to learn Python is connected to this bracket or to a period or to a comma. And the issue is that in terms of the training, there's like no actual requirement that these 30K dimensions make sense. So that, I mean, here it's really nice that we map learn to guide and learn to teach. But there's no actual requirement in terms of training that we have this nice synonym relationship. Disadvantage of this architecture that it's also a bag of words. So we have no word order. So flight London to Paris and flight Paris to London, they are mapped to roughly the same sparse vector and will retrieve the same results, even such that you want to retrieve different documents in this case.
Sorry, may I ask something?
Sure.
I missed how did we achieve this sparse vector with this projection? How do you achieve this sparse?
So you take the query, you pass it to BERT, and then you take, for example, the CLS token of BERT, which is like a 768 dimensional vector. Mm-hmm. And then you have an up projection to 30K. So you project these 768 dimensions to 30K dimensions. And then you add a sparse, like a sparseness operation that you go from a 30K dense vector to a 30K sparse vector by having a threshold. So you just say, okay, I just set values where the value is higher than a certain threshold. I don't know, like which are larger than 0, for example.
Okay, thank you.
Nils, I'm missing the motivation. Why would someone project upwards when you can have the dense encoders? I mean, you cannot even have the word order. I don't know why people came up with that.
Yeah. So the motivation was, I think why people came up with it is because the retrieval can be, or they claim it can be faster, which is not the case, or not necessarily the case. With dense vectors, the search in large vector spaces is really complicated. So if you have like 5 million or 500 billion points in this vector space, it's like a really complex operation how to find the nearest neighbor. And you need to use like different approximate nearest neighbor techniques to efficiently search in these dense vector spaces.
Yeah, I see.
Which is
but for the other one, when you have a binder vector, you already have different distances and you can use them. Yeah.
So for the other one, people claim that you can use inverted indices, which is like well known in information retrieval. So once people have invented TF-IDF 50 years ago, they invented inverted indices to search quickly through them so that they look, okay, here in the query, Python is relevant. Now give me all the documents that talk about Python. So they claimed that search is more efficient, but it's still a really big issue. So all the existing systems to search effectively for sparse encoders are really slow, because they were not really developed for this, and they also don't take into account modern hardware. But what's really interesting, what was found after these systems have been developed, is that sparse vectors are more robust to unknown words, which I will talk in a minute about, like the challenge of unknown words and how to represent them. And this makes them really interesting for me because they work a lot better if you do not have training data. So if you want to apply it to some domain to search for ACL paper in the ACL ontology, they work a lot more robust than dense models.
Interesting. Thank you.
Yes, so an overview of dense and sparse models. So dense models, they have like a low dimensional vector space, which are all non-zero. Sparse models have 30K or more dimensions. So some even go into like the millions of dimensions. They are mostly 0. The encoder for the query, you can, for dense, you always use like a transformer network. And for sparse, sometimes you just use the tokenizer, sometimes you use the transformer network. So here you can differentiate, do you want to have speed or do you want to have accuracy? Efficient search for dense vector space, you need to use some approximate nearest neighbor techniques. for sparse vectors, it's complicated because the systems we have like Elasticsearch or Ansarini, they do not work well with sparse vectors and are really slow. And state-of-the-art methods for dense, you can find them in sentence transformers, and in sparse, Splade version 2 is currently the best system for sparse vector spaces. And as Göster asked, like, okay, what's the motivation for sparse vectors? So I think this was found afterwards, but what I find really interesting is the challenge of unknown words. So as you know, our world is rapidly developing. And if you look on Twitter, on Archive or LinkedIn, there's like a new transformer architecture like every day. So there has been first BERT and then XLNet and Roberta and dBERTer and MPNet and MiniLM. And there's also Big BERT Pegasus. And the challenge when you have a dense encoder and you get a word like Big BERT Pegasus, like how do you encode it? So a dense vector space, as you know it from word embeddings, you have like similar words in the vector space. So here we have like different parts of a house. Here we have, I don't know, like things outside, saw, drill, tools. Here you have like how to color it, how to paint it. Where should you put this word in the vector space? It's also for human really, really hard. So if you don't know what Big BERT Pegasus is, it's really hard to put it meaningful in the vector space. And if you take a dense encoder and a state-of-the-art dense encoder and you look for the most similar words, the most similar words are big boss, big data, and big ass, which does not really make so much sense. So you would think like Big BERT Pegasus is a transformer architecture, so it should be connected to machine learning, deep learning, BERT, transformers, attention. But as the model doesn't know, it just looks at the word form and thinks, okay, Big BERT Pegasus is similar to Big Boss or Big Data and Big S. However, what happens if you put this into a sparse bi-encoder? The sparse bi-encoder, if you use a BERT network, it splits it into word pieces. And what's quite interesting is here it adds like related it adds weights to these word pieces. So it has like no idea what is Big BERT Pegasus, but instead of trying to find like the right place here in the vector space, just says, okay, I don't know. I just know these individual word pieces where I add a weight. Also, sometimes it adds related terms to it. So for example, maybe people misspell BERT with birds. So I add also some weight to the word piece birds, or big is a synonym for giant. So maybe someone is searching for giant BERT Pegasus. So it does not try to infer where to put it into a meaningful position in the vector space. It just says, I have no idea. So I just keep the word as is. And this is like really, really challenging for these bi-encoders. How do they handle these unknown words? So unknown words can either mean not seen during pre-training when you run masked language modeling, or also not seen during fine-tuning. And where should you put these words? Like you have Big BERT Pegasus, which is a transformer architecture. You have Klex chain, which is a cryptocurrency. You have Forward, which is a company from Israel, and you have this error code connected to Windows activation key. If you have no idea what these represent, it's like really hard to put them in a dense vector space. But for a sparse vector space, you don't try to do this. So if you see this error message, you just encode this in the sparse vector space, say this is a token. And if someone is searching for this error message, you will just retrieve this document. A big challenge that still remains for both systems are synonyms and related terms. So if the model have been trained in 2018, like the BERT network, it has no idea about coronavirus, COVID-19, or SARS-CoV-2. So it does not know that these are synonyms. And also, if you do it in terms of question answering and you ask the question, which vision transformer model is the best? And you have some text talking about VIT has been doing great in our experiment. If you don't know that VIT stands for vision transformer, it's really hard to retrieve this. So independent, if you use a dense or sparse encoder, they will not work for these scenarios because they have never seen it and does not know the relationship here. So I presented these different architectures, and what we wanted to do, we wanted to test a bit more systematically how well do they perform in an out-of-domain setting. So last year we created BEER, the benchmarking AR dataset, where we collected 18 datasets from different domains on different tasks, and we tested a lot of architectures, how well they perform. And first, if we compare dense bi-encoders, what we see is that they perform extremely well in domain. So we get like an 18-point improvement in domain compared to lexical search. But once you apply it to different domain like bioask or SciDocs, so bioask is biomedical question answering, SciDocs is on scientific publication, you see that these state-of-the-art models perform weaker than a simple lexical search baseline. And in fact, BM25 was better on 10 out of 18 datasets in the benchmark than a dense embedding model. We not only tested dense embedding models, but we tested a lot of architectures. The system that performed best was BM25 plus cross-encoder. So as mentioned, it's extremely good, extremely robust, but sadly extremely slow. And this doc2query or doc-T5 query performs also extremely well. And then we have these different dense embedding models or multi-vector embedding models that don't perform that well. What's missing in this plot is the sparse embedding model SPLATE2. It works for 12 out of 13 datasets. So the author sadly did not test it on all 18 datasets, just on 13 datasets. And here it worked better on 12 out of 13 datasets than lexical search. So the sparse models, they are also really robust. And once there's like a shift in the topics the documents are talking about. And then people studied this further. So they studied the inter and extrapolation performance. So interpolation is you have a train and test set, which is really similar. So your test queries, they just are a reformulation of your train queries. And then you have extrapolation where the train and test set is really dissimilar. And typically in search, you want to focus on extrapolation in most cases. So you're interested in the search queries which are new, unique, which you have not seen before. And they tested different architectures, cross-encoder, dense bi-encoders, and sparse bi-encoders on different training data sets. And what we see first is cross-encoders, they are the most robust. So if you train on a larger data set, you see basically no performance difference if your training and test data is similar or dissimilar. For dense bi-encoders, you see quite a big performance drop. So it goes from 66 NDCG to 59. And for sparse bi-encoder, you see that the performance drop is not as big. If training and test data is similar, you see that the dense bi-encoders, they work better as they can respect the word order and map it to the vector space. But as soon as there's like a shift in distribution, the sparse vectors work better. And then there's been also a nice study on that studied neural models for unknown rare terms, which was not seen during training. And all the neural models, they underestimate the importance. So if you search for really, I don't know, for big bird Pegasus and the model has never seen this word before, it underestimates the importance, so it will not find relevant documents. In contrast, lexical models, they overestimate the importance. So they see this word is like really rare. I don't have many documents, so I will just retrieve the 5 documents talking about this term, even such that other documents might be more relevant. So the perfect system would be somewhere in between of the two. So in the last part, I want to talk how you can adapt bi-encoders to new domains. So what we've seen, like all the architectures, they have an issue if they are applied to tasks and domains which they have not been trained on. And there are 2 different ways to do this. There's one, the adaptive pre-training, where you first pre-train on your target domain. So you run MLM on biomedical documents, and then you fine-tune on some labeled data you have. So for example, from MS Marco, this is a data set where you have Bing search queries and relevant documents from Bing. But this requires expensive training on labeled source data. So if you want to adapt it to a lot of different domains, you always have to first run pre-training and then fine-tuning again. So this is like really compute inefficient. And instead, what we want and what we developed last year is a way how you can flip it. So you can take a model that is fine-tuned on MS Marco, and then you can do unsupervised adaptation to the target domain. So this is a lot more compute efficient. And we called this system GPL, Generative Pseudo Labeling, which uses the different architectures I presented. So what we've seen is that doc to query is really robust, but sadly it's like inefficient. And we've seen that cross encoders are also really good and efficient, but also sadly really slow. So what we did, we took the best of these two, and we transferred the knowledge to an efficient bi-encoder. So how does GPL work? First, we have the generation phase. So we have the documents, we have the paragraphs from Wikipedia. For example, here, Python is a programming language. And then we ask a T5 model to create possible queries. What is Python? How good is the readability of Python code? So what could people search for where they would be happy to get this paragraph?
Nils, can I interrupt?
Yeah.
So how do you evaluate this? Is there an evaluation set for this doc to query thing? So we already have the documents and matched queries.
Yes, so we have the documents and matched queries. So from Microsoft, from the Bing search engine, we have 500,000 queries. So what people entered into Bing. And we have annotated documents which are relevant. And then you can just flip it. You say, okay, this is the document a person annotated as relevant. And then you train the T5 system to predict what has been the query, like what is Python. And then you can measure the perplexity of the T5 model. How well is it predicting the gold query the person asked? So
you're typically using natural language generation evaluation metrics.
Yeah, right.
Okay.
And then later you can test it in terms of like, does it improve your search system if you include it in with like lexical search?
Okay, thanks.
So now we have these different queries generated. Now we want to find like some negatives. So we have the query, the generated query, which programming language uses indentation. And then we search in our corpus of all paragraphs in Wikipedia, and we get like different paragraphs. I don't know, for example, Java is a class-based programming language. And then we use the cross encoder to score these different entries. So we have our query, we have the different alternative documents, and we ask our cross encoder to create a ranking, which is the most relevant one, which has the highest score and which has the lowest score. And why do you need the cross encoder? So the challenge is like twofold. First, it can be that the generated query is of really low quality. And the cross encoder will spot it, say, okay, this is my original positive document, and this is my generated query. It's of low quality, so I can just put like a low score to it. The other more challenging thing is like negatives. So if you search in the document for which programming language uses indentation, if you have a good search system, it will find relevant documents. So for example, in this example, we have the query, what is futures contract? And then you find in your document collection a paragraph about a future contract as a contract between party A and party B. So a human would judge this as relevant. And if you do train with standard cross entropy, where you say, okay, this is relevant, this is positive, these are negatives, this would like punish the system quite badly because this is like not a negative, it's a false negative. But the cross encoder correctly shows, okay, this is like a good hit for my query. This is a good hit for my query, while this hit is like quite bad, has like a quite low score. So here we can address for like noise in the data set, like noise in the query, generated queries, and noise in negatives. And then we can you train them with margin MSE loss. So you take the query, you take the positive document, you take the negative document, you pass it through the bi-encoder to get the vectors for all the 3 entries. Then you compute the dot score. So what's the similarity between the query and the positive, the query and the negative? And you compare the distance between these two to the distance of the cross-encoder. So if the cross-encoder thinks both are really similar in terms of the query, the distance will be small. If the cross-encoder thinks the positive document is so much better for the query than the negative document, then the distance will be large in the vector space. And so here the cross-encoder teaches the bi-encoder how should the vector space look like, what should be close in the vector space and what should be distant in the vector space. We evaluated on different data sets, on 6 different data sets, or in the latest version, even on 18 data sets. And we saw on the one side a really nice improvement on basically all data sets. But what's also nice is that's really compute efficient. So you start with your pre-trained model, which is available on sentence transformers, and you just start the training process. And the longer you train, the better the performance gets. So you don't have high computational overhead by adaptive pre-training, where you first need to run pre-training on the target domain, and then you train on your labeled data. But you can just plug it in, say whatever your compute budget is, train it for as many steps as you want, and you get an improved performance.
Nils, can you go back?
Sure.
So what does TSDAE stand for? Is this the previous state of the art? How did it work?
Yeah. So TSDE is a pre-training method also from my PhD student, Keixing Wang. It's a pre-training strategy. So masked language modeling, you mask certain words, but masked language modeling does not work well for embedding methods. In TSDE, we have a denoising autoencoder. So you encode, you take a passage, you delete some words in the passage, and then you encode it to a single vector. And then from this single vector, you decode it with a decoder to recreate the original passage without the noise. And this pre-training strategy is more suitable for embedding models, as it has like this embedding step in between, which achieves better performance for embedding tasks than MLM. And TSDE plus GPL is we just do this expensive pre-training with TSDE, then we do fine-tuning on MS Marco, and then we run GPL on our target domain again. So,
thank you.
So this is kind of an upper limit. Okay, conclusion. So dense models also have issues with unknown words. So they see a word and they have to put it somewhere in vector space, but they have like no idea where to put it. So they have no idea what is bi-encoders Pegasus and where to put it. Sparse embedding models, they can deal better with unknown words by just say, okay, I have no idea what bi-encoders Pegasus means. So I just keep it as a dimension in my vector space. But still they don't know, or it's unclear how you can update, how you can add synonyms, how does the model learn that coronavirus and COVID and SARS-CoV-2 and Omicron are all connected. So pre-training on the target domain and then fine-tuning on the source domain, for example, pre-training with MLM or TSDE can help, but it does not solve the issue fully. And also there's a high computational overhead. If you run this generative tool labeling, it gives you a nice performance increase without the need of labeled data. And also it's computational quite efficient. So it runs roughly 1 day on a V100 GPU. And you can stop it at any training step. So if you have less compute budget, you just train it for 25K steps, and you still get a nice improvement over your previous out-of-the-box model. And yeah, the code is available and documentation is available. So if you really want to take these embedding models, apply it to your specific domain on, I don't know, searching the ACL ontology, it works quite nicely. Thank you so much for listening.
Thank you.
Thanks a lot, Nils. This was a great presentation.
Yeah.
Nils was a lecturer in TU Darmstadt, and he always got like the highest evaluation scores. And I think this lecture again proved that. Okay, so we can get questions. If someone has any questions, please unmute yourself or write in the chat, and I can address it. Okay, maybe I can start, Nils.
Sure.
So you said that efficient and continual domain adaptation is still an open question mark. And what do you think would be the first steps to address that?
Yeah, so I think the challenge in domain adaptation are twofold. First, our language changes. So as mentioned, there are like new deep learning architectures every day. Also new companies or cryptocurrencies and whatever, new movies, books, they appear like every day. And the issues that we have in the transformer networks, they're like frozen in time. So if you ask a BERT network, who's the president of the United States, it will output that Barack Obama is the president. So the BERT network has no idea about Donald Trump, no idea about Joe Biden. And we as humans are amazingly efficient, data efficient. So if we read the news, Joe Biden is elected the new US president, we do so much update in our head in terms of our knowledge. So we know, okay, Donald Trump is no longer the president. Also, the first lady changes. Now Joe Biden is updated from former vice president to current president. Washington is no longer ruled by the Republicans, but by the Democrats. And we can infer all this knowledge from a single sentence, just reading Joe Biden was elected as the new US president. And somehow we have to get this up-to-date knowledge into transformer networks. So in search, we often search for the most recent events, most recent things. So for new companies, for new transformer architectures. And so we need some continual update of these transformer networks, which are also should be data efficient. So I should not present like, I don't know, 100,000s of documents on Big Bird Pegasus before the model learns what Big Bird Pegasus is. But it should be sufficient to mention at one to say, okay, Big Bird Pegasus is an architecture on an encoder-decoder architecture developed by Google. So this is the open question mark. How do we continue learning and also data efficient continue learning? And the second challenge is most cases, they focus on this setting where you do some pre-training like masked language modeling or auto-regressive text generation, and then they adapt it to like new data. But then you always need to fine tune again on labeled data. So what we really want is to take some model, which we have fine-tuned on our tasks. So we have fine-tuned it to do search. And then we want to inject new knowledge on new entities, on new concepts, on things that are different in the domain you're searching for. And yeah, that this is like big unsolved issue, which we're currently working on, but which is extremely challenging because networks are also extremely data inefficient. So if you run masked language modeling, you need a lot of data to learn new entities and what they mean and how they are connected. But for new entities, you don't have it. So you have maybe one paper talking about a new architecture, a new system. Like there's one paper talking about GPL, generative tool labeling, and you cannot efficiently run MLM on this because it's not sufficient amount of data.
Yeah, so yesterday at ACL, I mentioned there was a new session that's called STIR, Rising Stars. And it just reminded me of the talk by Ainsol Choi. Do you know her? She's an assistant professor at University of Texas. So she's doing a lot of work on enhancing the models dynamically. So basically using user feedback and having some interactive learning. And yeah, it sounds like an exciting research direction for us. And I think it has a lot of application domains, and information retrieval is just one of them.
Yeah.
I think question answering is another one, emergent one.
Yeah, totally agree. So an intern of mine is currently working on it, but it's super hard to find suitable evaluations and benchmarks for this, because often the benchmarks, they are also quite old. So I don't know, BERT has been trained on 2018 Wikipedia, and if you want to test it on new entities, so it doesn't know, I don't know, the different things you have in cryptocurrencies and blockchain and so on, you need some recent evaluation data set for that, but most often data sets are older than BERT. I don't know, on named entity recognition, they still use Wall Street journals from the 90s, or on different glue data sets, they are like from the early 2000s or 2010s. So what we would need is more recent evaluation data. And then also find evaluation data which focuses on new entities and new concepts. So if it still talks about what's the capital of the United States, this has not changed in like 200, I don't know, 70 years. But finding really data sets, it's extremely hard to find, and we haven't found any good data sets yet. So it would be quite interesting to create data sets here.
Yeah, it seems like there will be more data sets. I think several people are working on that now.
Yeah.
And maybe we can create models using historical texts. But that's also challenging.
Yeah.
Okay, are there any more questions or comments? All right, so let me thank Nils once more. It was great to have you, Nils, and I hope to have you. Oh, there's a question from Gürkan. Yeah, go ahead.
Thank you for the talk, Nils. So my question will be actually multimodal approaches. So we haven't talked much about them. So can you give more insight about them, and if you are working on them, like how can we improve the multimodal search? Because like I think same problems apply in that domain too, right? So how can we improve or like adapt them to new domains?
So multimodal models, here you can also do cross-encoders and bi-encoders. So if you do like a bi-encoder, you have like a different system for encoding the image. So for image, I don't know, you use a ResNet or you use a vision transformer, and for text, you use a BERT network. And there are also systems for cross-encoder where you encode the image and the text with cross-attention. And we also see that cross-encoder for image search are better than bi-encoders, so they are more robust and give better results. Domain adaptation. So I did not directly work on domain adaptation for images, but I could imagine that a similar approach could work comparably, that you have like some generation. So you take an image, you generate the caption, and then you take a cross encoder and you score the triplets. So I think the GPL system can also be applied to image search. I think what I personally find really interesting in terms of image search is like multilingual image search. So if you search for wedding and you search for it in English, then I don't know, you see like a woman in a white dress. But if you search for wedding in Chinese or in Hindi, they have like a different concept how a wedding looks like a Chinese wedding looks like different than an American wedding, looks different than a Hindi wedding. And here it can be interesting how you can fit in these cultural differences. Also in terms of food. So if you search in English for food, you maybe find a burger. If you search in Chinese for food, you find maybe some dish or some soup, like some Chinese dish. So how can you encode this in a vector space? It's quite interesting as a research direction, but I haven't seen so much work on this. So how can you include cultural properties and language properties into these vector spaces, because they tend to map everything to the same point. So if you search for a wedding, you find this one picture about the wedding, which is often like a US American type of wedding, but not like a Hindi or Chinese or Turkish wedding.
Yeah, I see. It's really interesting. So I'm working on something similar actually. So that's why I wanted to ask. Thank you.
Yeah, welcome.
Okay. Thanks a lot once more. If there are no last minute questions, let me close the seminar. And thanks a lot, Nils, for taking your time and informing us on neural search. I learned a lot today. And I hope to catch up soon at some place, sometime.
Yeah, hopefully. Right?
Yeah, hopefully. At TMNLP, maybe.
Yeah, maybe. But then in person, hopefully.
In person, definitely.
Yeah.
Okay. Thank you, and thanks for the participants and your attention also.
Great, thank you. Have a nice day, everyone.
You too. Bye-bye.